Torsional pendulum and damped oscillations. In this session, we will cover several key topics related to oscillatory motion. We will begin by exploring torsional pendulums, focusing on the restoring torque and the specific equations of motion that govern their behavior. From there, we will transition into an introduction to damped oscillations. We will examine the three primary types of damped motion: underdamped, critically damped, and overdamped. Finally, we will discuss how energy is dissipated in these real-world systems and look at the role of dampers in managing these oscillations. A torsional pendulum consists of a rigid object, such as a metal disc, suspended by a wire that is attached to a fixed support. When the disc is rotated or twisted through an angle represented by theta, the support wire is twisted as well. This wire then exerts a restoring torque on the disc that acts to pull it back toward its original position. This restoring torque is directly proportional to the angular position. Mathematically, the torque equals the negative of the torsion constant, represented by the Greek letter kappa, multiplied by the angle theta. Here, the torsion constant is a property of the wire that describes its stiffness against twisting. The diagram illustrates this motion, showing the disc oscillating through a maximum angular displacement. To understand how a torsional pendulum moves over time, we apply the rotational version of Newton's second law. This states that the sum of the torques is equal to the moment of inertia, capital 1, multiplied by the angular acceleration. By substituting our restoring torque expression, we find that the negative torsion constant times theta equals the moment of inertia times the second derivative of theta with respect to time. This leads us to the equation of motion, where the angular acceleration is proportional to the negative displacement. This defines simple harmonic motion. From this, we can determine that the angular frequency equals the square root of the torsion constant divided by the moment of inertia. Similarly, the period of oscillation is 2 pi times the square root of the moment of inertia divided by the torsion constant. Notably, this motion remains simple harmonic even for large angles, provided we stay within the elastic limit of the wire. While ideal systems might oscillate forever, real-world systems experience non-conservative forces like friction and air resistance. These forces retard the motion, causing the mechanical energy of the system to diminish over time. This lost energy is typically transformed into internal energy within the object or the surrounding medium. We call this type of motion damped. The image on the slide provides a classic example of a damped oscillator: a mass attached to a spring that is submerged in a viscous liquid. As the mass moves up and down, the liquid provides a resistive force that gradually brings the system to a halt. Damping is a vital concept in engineering and architecture. A famous example is the London Millennium Bridge, often called the Wobbly Bridge. On its opening day, the motion of many pedestrians caused the bridge to sway uncomfortably. To solve this, engineers installed over 50 tuned mass dampers beneath the structure. You can see these spring-loaded devices indicated by the red arrow in the photograph. These dampers work by capturing the mechanical energy of the swaying bridge and converting it into internal energy. This effectively reduces the amplitude of the oscillations, making the bridge stable and safe for public use. To model damped motion mathematically, we look at the retarding force. A very common type of retarding force is one that is proportional to the speed of the object. We express this as the vector r equals negative b times the velocity vector, where b is known as the damping coefficient. When we include this force in Newton's second law for a mass on a spring, the total force is the sum of the restoring force, negative k times x, and the damping force, negative b times the velocity. Setting this equal to mass times acceleration gives us a second-order differential equation: mass times the second derivative of position with respect to time, plus the damping coefficient times the first derivative of position, plus the spring constant times the position, all equals 0. When the retarding force is relatively small, specifically when b divided by 2 times the mass is less than the natural frequency, we have underdamped motion. In this case, the system still oscillates, but the amplitude decays over time. The position x is described by the initial amplitude multiplied by an exponential decay factor, which is e raised to the power of negative b divided by 2m times time, all multiplied by a cosine function. The angular frequency of this damped motion is slightly less than the natural frequency. It equals the square root of the quantity k over m minus the square of b over 2m. As shown in the graph, the red oscillating line stays within a dashed envelope that shrinks exponentially as time passes. We categorize damping into 3 distinct types based on the strength of the resistive force. First, underdamped motion, shown by the blue curve, occurs when the damping is low, allowing for oscillations with a decaying amplitude. Second, we have critically damped motion, represented by the red curve. This happens when the damping coefficient reaches a specific critical value, where b divided by 2m equals the natural frequency. In this state, the system returns to equilibrium as quickly as possible without any oscillation. Finally, overdamped motion, shown by the black curve, occurs when the damping force is very large. In an overdamped system, the object also returns to equilibrium without oscillating, but the process is much slower because the high viscosity or friction drags out the return time. In summary, we have seen that torsional pendulums generate oscillatory motion using a restoring torque that is proportional to angular displacement. We also learned that real oscillators are almost always damped by non-conservative forces such as friction, which leads to a loss of mechanical energy. This energy is not destroyed but is instead transformed into internal energy. We classify this damping into 3 categories: underdamped, where the system still oscillates; critically damped, where it returns to equilibrium fastest; and overdamped, where the return to equilibrium is slow and sluggish. Each category is determined by the value of the damping coefficient B relative to the system's mass and spring constant. To conclude, let us consider 2 review questions to test your understanding. First, think about the period of a torsional pendulum. Based on the formulas we discussed, how exactly does that period change if you increase the moment of inertia of the disc, or if you use a stiffer wire with a higher torsion constant? Second, describe the physical difference between critically damped and overdamped motion. Specifically, if you were watching a system return to its equilibrium position, how would the timing and behavior differ between these 2 states? Reflecting on these will help solidify the mathematical and conceptual links we have explored today.